Hello everyone, welcome to this KANPUR-NPTEL online course on space environment and its effects on orbital spacecrafts. So, in this module we are discussing the risk assessment and the reliability and the quality assurance of the spacecraft material, components, system and subsystems. So, in the last session we discussed or we defined what is the reliability and the unreliability functions, and we said that is the whenever the reliability is basically the probability that a engineering system or it can be a subsystem or component will perform for the designated or the intended life under the given environmental conditions. And in this regard we defined also the unreliability. So, unreliability also it is the probability of having the system in a failed state f t at time t, that means the failure has occurred between the time 0 to t, and this is the complement of reliability. So, I can write that is R t plus f t, that is the this is a binomial type of yes or no. So, the if I consider this is the event space. So, event space consists of the events which are failed or which have succeed. So, if I add the probability of these two probability, I should get 1. Then we defined that is the failure probability density function. This is a density function f t. So, how we get a probability density function when I have the cumulative probability function. So, thus to differentiate it. So, if we have the that is the probability of failure, that is the f t, that is the cumulative probability function, then I can find the probability density function just by differentiating this with respect to time, and then it gives me since here the time is my variable, the random variable. So, it is the derivative with respect to time, and if I use these equations. So, this failure density function will be equal to that is minus of the derivative of the reliability function. So, if you want to know that is the what is the probability of failure occurring during a time interval, then suppose you want to know what is the probability it is happening, it can happen between 0 to t. So, you have to integrate that probability density function from 0 to t, then this integrated value will give you the probability of failure. Then we defined we discussed yesterday or it is in the last class, that is the failure rate, or we call it a hazard rate also, hazard rate. So, it is related to the failure probability density f t, and this also we derived yesterday, that is the failure rate or the hazard rate is given by the probability that is failure probability density function divided by the reliability function. Now, f t is already we have it is minus d r by d t. So, I can write h t d t is equal to minus d r by d t. So, this much we did yesterday. So, we will proceed with this. So, today we will discuss what is the significance of the hazard or failure rate, followed by the reliability in terms of failure or hazard rate, then failure rate and the bathtub curve. This is very important the curve used in reliability engineering, that is called the bathtub curve. We will discuss that. So, failure rate, that already we have found out an expression for that failure rate or hazard rate. So, this is related to two types of breakdown that can or the failure that can happen. So, we will consider here our the spacecraft, that is the system related to the spacecraft. So, it can be coincidental or accidental breakdown. This is one way. What is the example? The example is heating by hypervelocity, impact of the particulates available, particulates. So, or it can be the arcing due to the geomagnetic storm. We have seen when the geomagnetic storm is there, the spacecraft gets charged. So, there can be arcing. So, this type of breakdown, if it happens, these are the coincidental or accidental. The other type, the breakdown which results from the usage. Okay. Usage means you are using it and then there will be that's end of life will come when. So, the example like that that is the wear of the mechanical devices such as bearings, and there is the momentum wheel, then the degradation of the like we are using the cathodes of the travelling wave tubes TWTA, or the the exhaustion of the energy sources as for example, the propellant required for the station keeping and attitude control. So, when these things happens, we call it the end of life, and we will see that the failure rate the failure rate will be different for both the cases. That we will see when we will discuss the bathtub curve. So, what is the failure rate? Failure rate is the frequency with which a subsystem or a system or component fails. This is expressed in failures per unit of time. Okay. And so, we have denoted it by h, in some books it is written by lambda. We will also use this term when we will consider a constant failure rate. So, this is called this HT1 is a function of time. So, we call it say instantaneous failure rate HT of a given piece of equipment. It is defined as the limit as the time interval tends to 0 of the ratio of the number of pieces of equipment which fail in the time interval concerned to the number of pieces of the equipment in a correct operating state at the start of the time interval. So, you have seen yesterday when we derived it, we have taken that, we have considered there is some the number of components at t is equal to 0 n, and then we considered at some time t there are some components that fail. So, from there we wrote that is the first we defined the probability, and using the binomial the distribution we wrote the what is the probability, and then from there integrating that probability function we derived this thing. So, whatever we have derived, exactly the same thing is written here. Okay. So, here a large number of identical pieces of equipment is assumed to operate at the same time. So, this is whenever we do whenever we have derived or whenever the failure rate, this is the condition. Okay. So, we have already derived, that is the expression for hazard failure rate So, it is H t is given by F t divided by R t. Here F t is the probability density function of the failure. So, this we can write as minus R dash, that is the derivative of the reliability function divided by the reliability function. So, this we could write because F t is given by the minus of the derivative of the reliability function. Okay. So, this I can write as minus 1 by R t, and R dash t is d r by d t. So, now we can rearrange this equation and write d r by d t divided by R t, this is equal to minus H t into d t. So, now we will integrate both the sides, of this equation. of this equation with the limit. So, the limit will be r t 0 which is equal to 1 to r t in the left hand side and 0 to t in LHS and RHS respectively. So, if I do that, then I should write integration, then I can write 1 to r t, then d of r t by r t. So, this is equal to minus 0 to t h t d t h t and d t. So, here this is 1 because as I already says r of 0, this is basically r of 0. So, this r of 0 is equal to 1, r of 0 to 0 to t. So, now I can write 1 to r t, then d of r t divided by r t So, this is equal to minus integration 0 to t h t d t. Now, if you integrate d r t by d t, then it will give you the natural logarithm of r t. So, this is ln of r t, then 1 to r t, this is equal to minus 0 to t h t d t. So, this you will get. So, ln of 1 is 0. So, I can write this ln of r t is equal to minus 0 to t h t d t, and now I can write r t is equal to exponential and within bracket 0 to t h t d t. So, now we can notice one thing, that is the integration of, if I do 0 to t h t d t, it will tend to 0 when t tends to 0. So, what does it mean? That r of 0 is equal to exponential 0, so which is equal to 1. So, that already we said, that is at the beginning all the elements are working. So, the reliability is 1. Now, 0 to t h t d t, it will tend to infinity when t tends to infinity. So, r of infinity will be exponential minus infinity, that is equal to 0. So, no components can work up to infinite times. So, its reliability has to be 0. So, that is proved from this expression. That is, we will define the same thing in on the other way and try to explain what actually the this hazard rate or the failure rate in terms of probability, what does it mean. So, I can we can assume that the probability that a failure occurs between between the interval t1 to t2, given that no failure occurs before T1. So, here is a condition. So, I am telling the probability that a failure occurs between T1 to T2 given that no failure occurs before T1. So, this is some sort of a conditional. So, it is known as the conditional probability. So, I can write this as R of T1 minus R of T2 divided by T2 minus T1 into R1 T. So, this is basically this is our failure rate. So, probability that the failure occurs. So, it is failure occurs per unit time. Okay. So, now what I will do, we will put T1 is equal to, so we will put T1 is equal to T and T2 will put as T plus delta T. So, just we are writing in terms of the a short time interval delta T. So, if I do that, so this is my H T. So, the H 2 will be equal to it will be R T minus R T plus delta T divided by delta T into R T. So, here what we are doing, we are interpreting thus the failure rate can be interpreted as a conditional probability density function that a system or component fails in a small time interval given that it has served performance at the beginning of the interval. So, we will write it. So, what is conditional probability actually? So, conditional probability, just for your recapitulation, conditional probability. So, conditional probability that the occurrence of an event A or B, given that A has already occurred, it is given by the probability of the intersection of A and B divided by P A. So, we can show similarly this one also H T also. So, what we have written H T is R T minus R T plus delta divided by delta T into R T. Okay. So, we will now write again in terms of the standard the way we write it, the probability function. So, we will write it like that. So, if we know that a component was functioning up to time t, then the probability of failure within time interval delta t, that we can write is P, we will write it like. So, this event we are that is the failure event, we are writing it like x. So, it happens between t and t plus delta t, given that it has already performed up to t. So, I can write it like this. So, we will put it like this, second bracket. Okay. So, this I can write, how I can write it? So, I will use this. So, I can write it P, that event x belonging to t comma t plus delta t, then union of x, not union, intersection of x greater than t. Okay. So, and then it will be divided by p x of t, x greater than t. So, the same thing I can write in this form, So, I can write it R T minus R T plus t plus delta t divided by R T. So, what is this actually? What this will be equal to H T into delta t. So, so I can integrate over this and get this is the probability that whether it will perform or not. Okay. So, now what is our that is the expression for reliability function? This is R T is equal to exponential minus integration 0 to t H t dt. Now, let us assume that this H t is constant with time. So, if we assume H t is constant, which is equal to lambda, then I can show that this. So, this if I do this integration 0 to t then lambda dt. So, this will give me lambda t. So, then my this function becomes R t dt. So, this reliability function will become exponential or e to the power minus lambda t. Okay. So, this is called the exponential probability function. So, if I want to find the failure density function, failure rate is this one. So, if I want to find f t, then f t I will differentiate this dRt by dt, which will give me lambda e to the power minus lambda t. Okay. So, this is called the exponential probability density function, exponential PDF. So, you see this for constant failure rate, we had R t is equal to e to the power minus lambda t. So, you see whenever this lambda is very small value, now you can say it will have the life will be longer whenever the failure rate lambda is smaller. And so, now we will define a very important the curve that is called the bathtub curve. So, this one is called the bathtub curve. So, what it is? So, you see this is the failure rate. So, I can write it H t, and you see the failure rate is constant here. So, we will define the term here, maybe this T 1 and this is T 2. So, from 0, so this is 0, that is it is starting. So, from the start of operation to up to time T 1, the failure rate is decreasing, then it is constant, almost constant, then it is again increasing. So, this curve is called the bathtub curve, and basically it is used for basically for the electronic components or the system. This early period is also called the mortality period, infant mortality period. This is also called the infant mortality period. This is also called infant and this is the wear out at the end. And so, we will in the next class we will continue from this, and that is the what is the significance of this bathtub curve, and how we can for this part actually the infant mortality or the early failure period, wear out period, how we can write the expression for the failure rate, that we will see. Okay, thank you very much.